In 2015, humanity threw a dart at the edge of the solar system. A machine the size of a grand piano, wrapped in gold foil and bristling with sensors, screamed past the dwarf planet Pluto at 1,000 miles per hour. It had traveled for nearly a decade to get there. It covered 3 billion miles of empty, silent void. And when it finally arrived, after all that time and all that distance, it did not stop. It could not stop. To hit the brakes would have required more energy than the rocket that launched it. So it flew by. It snapped a few thousand photographs, measured the thin, freezing atmosphere, and then continued into the dark, vanishing into the Kuiper Belt forever. We celebrate the New Horizons mission as a triumph of engineering, and it was. But it also revealed a haunting truth about our place in the universe. We can send our robots to the edge of the system, but only if they are light, only if they are fast, and only if they never intend to stay. When we talk about sending human beings to Pluto, we often think of it as a scaling problem. We assume that if we can go to the moon in 3 days, and if we can plan a trip to Mars in 6 months, then Pluto is just a matter of adding more fuel and waiting a little longer. We imagine it is like driving a car across a continent instead of just across town. But the universe does not work like a highway. The physics of the outer solar system are fundamentally different from the physics of the inner planets. The rules change, the scale changes, and most importantly, the energy cost changes. To understand why a human foot-hand forint may never be pressed into the nitrogen ice of Pluto, we have to peel back the layers of our own ambition and look at the raw, cold mathematics of space travel. We have to confront the tyranny of the rocket equation, the silence of the light, speed limit, and the absolute crushing weight of the energy required to keep a biological organism alive in the dark. This is not a story about lack of funding. It is not a story about political will. It is a story about the limits of thermodynamic reality. If you are ready to explore why the edge of our home system might remain a ghost town forever, make sure you are subscribed and settle in. The journey we are about to take is long, cold, and quiet. Let us begin with the geometry of the void. When you picture the solar system, you likely imagine a series of concentric rings, like ripples in a pond, with the sun in the center and the planets marching in orderly circular paths. In this model, Pluto is just the furthest ring. But this mental map is a deception. Space is not a flat sheet of paper, and orbits are not perfect circles. Pluto does not sit at a fixed distance from Earth. It is a moving target in a 3-dimensional ocean of emptiness. Its orbit is wildly elliptical, a stretched-out oval that sends it swinging deep into the darkness and then diving back toward the sun. At its closest point, called perihelion, Pluto is about 2.7 billion miles from the sun. At its farthest, called aphelion, it drifts out to 4.6 billion miles. That difference alone, the gap between its closest and furthest points, is nearly 2 billion miles. That is roughly the distance from Earth to Uranus. Depending on when you choose to launch, the journey could be vastly longer or shorter. But the geometry gets worse. Pluto does not orbit on the same plane as the rest of the planets. Earth, Mars, Jupiter, and the others all orbit roughly on a flat disk, like marbles rolling on a table. Pluto is different. Its orbit is tilted by 17 degrees. To reach it, a spacecraft cannot just travel outward, it must travel upward, climbing out of the gravitational well of the solar ecliptic. This inclination is the first assassin of mission planning. In spaceflight, changing your direction is expensive. Changing your plane is excruciatingly expensive. Every degree of inclination change requires a massive expenditure of fuel. You are fighting the momentum of your own launch, canceling out your existing velocity vector and building a new one. To climb 17 degrees out of the solar plane to catch Pluto requires an energy budget that dwarfs a mission to Mars. It is like trying to merge onto a highway that is not only miles above you, but also twisting at an angle to the ground. You cannot just steer, you have to burn. And every second you burn your engines, you are using propellant that you had to carry with you from Earth. This brings us to the concept of the launch window. Because Earth and Pluto are both moving, and because they move at vastly different speeds, the alignment required for a fuel, efficient transfer happens rarely. Earth races around the Sun once every year. Pluto takes 248 Earth years to complete a single lonely circuit. This means Pluto is effectively stationary compared to the whirling motion of the inner planets. Mission planners have to wait for the planets to align in a specific configuration where a spacecraft launched from Earth will intercept Pluto years later. If you miss that window, you do not just wait a few days, you might wait decades. New Horizons launched in 2006. It utilized a gravity assist from Jupiter to gain speed, stealing a tiny fraction of the giant planet's momentum to fling itself outward. That alignment, Earth, Jupiter, Pluto, was a rare celestial gift. Without Jupiter, the trip would have taken years longer. If we were to launch a crewed mission, we would need a similar alignment to make the journey survivable. But humans are heavy. Our life support systems are heavy. Our water, our air, our radiation shielding it all adds mass. A gravity assist that works for a piano-sized robot barely makes a dent in the trajectory of a massive starship. The massive ship would need to bring its own energy, its own propulsion, and that mass penalty begins to spiral out of control before the rocket even leaves the launch pad. Consider the sheer scale of the distance. 3 billion miles is a number so large it loses meaning. Let us measure it in time. Light, the fastest thing in the universe, travels at 186,000 miles per second. A beam of light leaving Earth reaches the Moon in 1.3 seconds. It reaches Mars in anywhere from 3 to 20 minutes. But to reach Pluto, light has to travel for 5.5 hours. This dictates the first profound psychological horror of a human mission to Pluto, the silence. Imagine you are the commander of this hypothetical vessel. You are billions of miles from home. Something goes wrong. Maybe a seal on the air recycler fails. Maybe a thruster valve freezes. You send a distress signal to Earth. You speak into your microphone, your voice traveling at the speed of light. You say, "Houston, we have a problem." Then you wait. You wait for the signal to cross the abyss. 1 hour passes, 2 hours. The signal passes the orbit of Jupiter, 3 hours. It passes Saturn, 4 hours, 5 hours. Finally, 5.5 hours later, your voice reaches the deep space network antennas in Australia or California. The flight controllers on Earth hear your distress call. They immediately convene a meeting, analyze the data, and come up with a solution. Let us say they are incredibly fast and solve the problem in 30 minutes. They transmit the instructions back to you. Now, the answer has to travel the same distance back. Another 5.5 hours. In total, 11.5 hours have passed since you asked for help. In a true emergency, in a fire or a depressurization event, 11 hours is an eternity. You would be dead long before the reply arrived. This means the crew must be completely autonomous. There is no mission control in the traditional sense. There is only the crew, the ship, and the void. The psychological weight of that isolation is difficult to model. On the Moon, Earth is a giant blue marble hanging in the sky, comforting and close. On Mars, Earth is a bright star, a visible reminder of home. At Pluto, Earth is invisible. It is lost in the glare of the sun, which itself has shrunk to a piercingly bright point of light, indistinguishable from other stars to the naked eye. You are not just far away, you are disconnected from the visual reality of your origin. This distance also creates a problem that engineering struggles to solve: navigation. In the inner solar system, we track spacecraft using radio signals. We send a ping, the spacecraft pings back, and we measure the time delay to calculate distance and speed. We use the Doppler shift of the radio waves to measure velocity. But at Pluto distances, the precision of these measurements degrades. The beam of radio waves spreads out, becoming weaker and wider. The noise of the cosmic background interferes. Navigating a ship into orbit around a moving target 3 billion miles away with an 11-hour command delay requires a level of onboard artificial intelligence and autonomy that we are only just beginning to develop. The ship must know where it is going, and how to fix its own course without human intervention from the ground. But the isolation is only the beginning of the energy problem. The deeper issue, the one that governs life and death, is the sun itself. All human life on Earth is solar, powered. Our food comes from plants fed by sunlight. Our weather is driven by solar heat. Even our fossil fuels are just trapped, ancient sunlight. In space, we rely on solar panels to harvest this energy. The International Space Station runs on massive wings of solar cells that drink in the abundant light of Earth orbit. Even probes to Jupiter, like Juno, can manage with massive solar arrays because the sun, while dimmer, is still potent. However, light follows an inverse square law. If you double your distance from the sun, the light intensity drops to 1/4. If you triple the distance, it drops to 1/9. By the time you reach Pluto, you are roughly 40 times further from the sun than Earth is. The math is brutal. 40 squared is 1,600. The sunlight at Pluto is 1/16, hundredth as intense as it is here. A solar panel that generates 1,000 watts on Earth would generate less than 1 single watt at Pluto. It would be useless. Dead weight. This means a human ship to Pluto cannot use solar power. It cannot use the free energy of the star we orbit. It must carry its own power plant. It must bring a nuclear heart, a reactor capable of generating electricity for decades without refueling. And not just a little electricity. We are not talking about the trickle of power needed to run a camera or a radio on a robotic probe. We are talking about the massive power loads required to keep human beings alive. Humans are fragile, wet, warm machines. We need oxygen scrubbers running constantly. We need water recyclers boiling and condensing fluid 24 hours a day. We need thermal heaters to keep the cabin from freezing into a crypt. We need artificial lighting to grow food, or just to keep our circadian rhythms from collapsing into madness. We need kilowatts, hundreds of kilowatts, continuously, for 20 years. That energy requirement dictates the mass of the ship. A nuclear reactor is heavy. The shielding required to keep the radiation from that reactor from killing the crew is even heavier. The cooling radiators needed to dump the waste heat from the reactor into the vacuum are massive structures. And suddenly we are back to the rocket equation. Because the ship is heavy with reactors and shielding, it needs more fuel to move. Because it has more fuel, it is heavier, so it needs even more fuel to move that fuel. The spiral begins. The cold of the outer solar system is not like a winter day on Earth. It is a fundamental absence of energy. The background temperature of deep space is roughly 2.7 Kelvin, just a whisper above absolute zero. At Pluto, without the warming touch of the sun, the hull of your spacecraft wants to reach thermal equilibrium with that void. It wants to freeze. Every lubricant in every mechanical joint wants to solidify. Every battery wants to stop chemical reactions. The very air inside the ship wants to turn into liquid and then into ice. On the International Space Station, the problem is usually getting rid of heat. The station sits in direct sunlight and is full of electronics and warm bodies, so it has to radiate heat away to keep from cooking the crew. But as you travel outward, past Mars, past the asteroid belt, past Jupiter, the equation flips. You cross a thermal threshold where the battle is no longer about staying cool, it is about staying warm. By the time you reach Pluto, the ship is bleeding heat into the blackness at a terrifying rate. The insulation required is thick and complex. The energy needed just to run the heaters rivals the energy needed for propulsion. You are fighting entropy in its purest form. The universe wants your ship to be cold and dead. You have to burn nuclear fuel just to insist that you remain warm and alive. And then there is the duration. This is the variable that truly breaks the human spirit. How long does it take to get to Pluto? New Horizons took 9.5 years traveling at record, breaking speeds. But remember, it didn't stop. To stop, you have to slow down. To slow down, you have to approach slowly, or you have to burn massive engines in the opposite direction. If we want to put humans into orbit around Pluto or land on it, we cannot fly by at 30,000 miles per hour. We have to arrive gently. This means the trip takes longer, much longer. With current chemical propulsion, the fire-breathing rockets we use today, a mission that stops at Pluto could take 20 to 30 years. One way. A round trip would consume an entire adult human life. An astronaut would leave Earth in their 30s, in the prime of their physical health, and return, if they returned at all, as an elderly person, their bones brittle from decades of microgravity, their eyes damaged by cosmic radiation, their memories of Earth fading into a dream. Who would volunteer for such a mission? It is effectively a prison sentence in a tin can. But even if we found volunteers, The sheer logistical weight of keeping them alive for 40 years is staggering. Think about the food. The average human eats about 4 pounds of food per day. Over 40 years, for a crew of 6, the food alone would weigh hundreds of tons. You cannot grow all of it. Space farming is energy, intensive, and risky. If a crop fails, the crew starves. So you have to pack preservatives. But vitamins degrade, nutrients break down. After 10 years, your food stores might still provide calories, but they would be nutritionally hollow. The crew would succumb to scurvy or other deficiencies long before they reached their destination. This is the tyranny of the biological payload. A robot can hibernate. It can shut down its systems, freeze, and wake up 10 years later with a simple electrical command. A human must burn energy every single second. A human is a fire that must be fed. We inhale oxygen and exhale carbon dioxide, constantly polluting our own small ecosystem. We excrete waste that must be processed. We require psychological stimulation. We require gravity, or at least simulated gravity, to keep our hearts from shrinking and our bones from dissolving. All of these needs add mass. All of that mass fights the propulsion systems. All of that propulsion requires energy we do not have. The concept of a fast trip to Pluto is a relative term. To cut that travel time down from 30 years to maybe 10 years, we would need engines that do not yet exist. We would need propulsion systems that are orders of magnitude more efficient than the best chemical rockets ever built. We often hear about nuclear thermal rockets or ion drives as the saviors of deep space travel, and they are incredible technologies. But even they run into the hard limits of physics when you stretch the destination out to 3 billion miles. Ion engines are efficient, sipping fuel like a fine tea, but they are incredibly weak. They push with the force of a single sheet of paper resting on your hand. They need years to build up speed, and they need massive amounts of electricity to run electricity that, as we established, cannot come from the sun. So now you need a massive nuclear reactor to power the ion engines to push the massive ship. The snake eats its own tail. Nuclear thermal rockets, which use a reactor to superheat hydrogen gas, offer high thrust and reasonable efficiency. They are the best hope we have for Mars. But for Pluto? The problem becomes the hydrogen itself. Liquid hydrogen is a nightmare to store. It boils off. It leaks through the microscopic pores of metal. Keeping hydrogen liquid for a 10 or 20-year mission is an engineering challenge that we have not solved. You would launch with full tanks and arrive at Pluto with them empty, the fuel having simply evaporated into the void along the way. We are trapping ourselves in a box defined by energy density. Chemical bonds, the burning of fuel, can only release so much energy. There is a ceiling. We hit that ceiling in the 1960s. We have refined it, polished it, and made it slightly better, but we haven't broken through it. To reach Pluto in a reasonable time frame, to make it a place humans can actually visit, we need new physics. We need energy densities that look more like stars than campfires. But until we have that, until we can harness the power of the atom in a way that is light, stable, and incredibly potent, Pluto remains behind a wall. It is a wall built of distance, yes, but the bricks are made of joules and watts. The mortar is the unyielding math of mass ratios. We look at the beautiful images sent back by our robot envoys, and we project our own longing onto those frozen plains. We name the mountains after our explorers. We name the dark patches after our myths. We want to be there. We want to stand on the edge of the nitrogen glaciers and look up at the faint, distant sun. But the universe does not care about what we want. It only cares about what we can pay for. And the price of a ticket to Pluto is currently higher than the energy budget of our entire civilization can afford to allocate to a single ship. As we stare out into that abyss, we must realize that the first step to conquering the outer solar system isn't building a bigger rocket. It's understanding the fundamental currency of the cosmos: energy. Without it, we are just drifting. And out there, in the dark, drifting is a death sentence. If you are fascinated by the impossible boundaries of our universe and want to understand the physics that keeps us grounded, hit that like button and subscribe. We are just getting started. In the next part of our journey, we will look closer at the engines themselves, the roaring beasts of fire, and the silent streams of ions, and see exactly why they fail us when the destination is the underworld. The math is about to get even darker. On Earth, we are addicted to the instant. You tap a glass screen, and a message appears on the other side of the planet. You speak a command, and a machine responds. We have built our entire civilization, our economy, and our sense of safety around the assumption that connection is immediate. If you fall, you call for help. If you are lost, a satellite finds you. We live in a bubble of real, time interaction where the speed of light is so fast compared to the distances involved that it might as well be infinite. But as we drift outward from the Earth, past the Moon, past Mars, that bubble begins to stretch. And when we reach the distance of Pluto, the bubble bursts. The speed of light, which feels instantaneous here, reveals itself for what it truly is, a crawl, a slow, agonizing limit that transforms communication into history. To understand the terrifying reality of a human mission to Pluto, you must stop thinking about distance in miles and start thinking about it in lag. The delay is not a technical nuisance, it is an existential wall. When a spacecraft at Pluto transmits a signal, that radio wave travels at 186,000 miles per second. It races past the orbit of Neptune, past Uranus, past Saturn. It takes hours. By the time that signal reaches the deep space network antennas in the California desert, 5.5 hours have passed. The flight director hears the voice of the astronaut, but they are hearing a ghost. The voice they hear spoke 5 hours ago. The astronaut who spoke it has already lived another 5 hours of life, taken thousands of breaths, perhaps solved the problem, or perhaps died. Imagine a critical failure. A seal blows on a pressure hatch. An alarm screams in the cockpit. On the International Space Station, the astronauts would immediately talk to Houston. Ground control would see the telemetry instantly. They would say, switch to backup bus B or isolate the leak. The crisis would be a shared event, a collaboration between the crew in the sky and the thousands of engineers on the ground. At Pluto, that collaboration is impossible. The crew screams for help. Their telemetry streams out into the void. But for 5.5 hours, the screens at Mission Control remain green. The flight controllers are sipping coffee, chatting about the weather, completely unaware that their crew is fighting for their lives billions of miles away. The catastrophe has already happened. The outcome is already decided, and the people on Earth are watching a phantom data stream from a past that no longer exists. If Mission Control finally receives the alarm and instantly calculates the perfect solution, they transmit the command. That command takes another 5.5 hours to return. The total round trip time is 11 hours, 11 hours of silence. In a fire, in a depressurization, in a medical emergency like a heart attack or a stroke, 11 hours is not a delay. It is a death sentence. This dictates that a crew traveling to Pluto must be totally, terrifyingly autonomous. They cannot rely on Earth for decisions. They cannot rely on Earth for comfort. They are effectively a separate civilization of 6 people, drifting in a life raft on an ocean so wide that the shore has been forgotten. This isolation breeds a psychological pressure that we have no data to model. We have put humans in isolation experiments on Earth, in caves, in Antarctic research stations during the long winter night. But in those scenarios, the participants know that if things get truly desperate, a helicopter can come. A door can be opened. The air outside is breathable. At Pluto, there is no rescue. There is no abort. Once you burn that engine for the trans-Neptunian trajectory, you are committed to the darkness for decades. And the darkness itself is different there. On Earth, we have a sky. Even at night, we have the moon, the stars, the glow of cities. On the moon, the astronauts had the Earth a beautiful, fragile blue marble hanging in the blackness, a constant reminder of life and warmth. It was the psychological anchor that kept them sane. They could look up and see home. On Mars, Earth is a bright star, a morning star or an evening star, visible to the naked eye. You can point to it and say, "That is where I was born." But at Pluto, The geometry of the solar system conspires to steal your home from you. Earth is so close to the sun, and Pluto is so far away, that looking back at Earth means looking directly into the glare of the star. From the surface of Pluto, Earth is lost in the solar corona. It is invisible. You cannot see it. You cannot point to it. For 20 years, the crew would look out of the portholes and see only the static, unblinking field of stars. The psychological effect of this Earth loss is profound. It is a severing of the visual tether. You are not just far away, you are unanchored. You are floating in a void where your origin point has ceased to exist as a visible object. You are a creature of the dark, and it is dark. We call it the solar system, implying that the sun rules everything. But out there, the sun is an imposter. It has shrunk. It is no longer a disk in the sky. It is just a piercingly bright point, like an arc, welder's spark seen from across a stadium. It provides no warmth. It provides very little light. Noon on Pluto is not day. It is a permanent, eerie twilight. It is roughly as bright as Earth shortly after sunset, the moment when you can still read a book if you squint, but the colors have drained out of the world and everything is turning gray. This perpetual twilight creates a biological havoc. Human beings evolved in the rhythm of day and night, of bright blue, sky noon, and dark sleep. We have circadian rhythms coded into our genes. Without the strong cue of bright sunlight, those rhythms drift, sleep cycles shatter, depression sets in. The crew would need artificial suns, massive banks of full-spectrum LED lights lining the walls of the ship to trick their brains into believing they are still on Earth. But lights require power, and power is exactly what the darkness steals. This brings us to the death of solar energy. The history of space exploration is the history of solar panels. They are elegant, silent, and reliable. They have no moving parts. They just sit there and drink photons. The Juno spacecraft at Jupiter has 3 massive solar wings, each the size of a tractor-trailer, to catch the dim sunlight 500 million miles from the sun. But Jupiter is the limit. Beyond Jupiter, the curve of intensity falls off a cliff. The inverse square law is a cruel master. Because the sunlight spreads out in a sphere, its density drops with the square of the distance. At Pluto, the solar flux, the amount of energy hitting a square meter, is about 1 watt. On Earth, it is over 1,300 watts. To generate enough power to run a coffee maker at Pluto using solar panels, you would need an array the size of a football field. To run a life support system for 6 humans, you would need panels the size of a small city. They would be so large and so fragile that the slightest maneuver of the ship would tear them apart. They would add so much mass that the ship would be impossible to move. So, solar is dead. We have to bring our own fire. We have to carry nuclear energy. In robotic missions, we use devices called radioisotope thermoelectric generators, or RTGs. New Horizons had one. Voyager had them. They are simple, rugged nuclear batteries. They use a slug of plutonium-238, which is naturally hot because it is decaying, and they use thermocouples to turn that heat into electricity. They are reliable, but they are weak. The RTG on New Horizons produced about 240 watts at launch. That is enough to power 2 standard light bulbs. It was enough for the robot because the robot was asleep for most of the journey, and when it woke up, it only needed to power a camera and a hard drive. Human beings are not cameras. We are energy sinks. We need kilowatts. We need heat. We need air recycling. A human mission would need a power source hundreds of times more powerful than an RTG. We would need a full fission reactor, a nuclear power plant in space. We have built these on paper. We have tested small ones on the ground. But flying a megawatt-class reactor to Pluto is a nightmare of engineering contradictions. First, the reactor is heavy. It needs shielding lead, tungsten, or water to protect the crew from the neutron radiation it spews. If you don't shield it, the reactor that keeps you warm will also give you cancer in a month. So you add tons of shielding. Now the ship is heavy. Now you need more propellant. But worse, a reactor generates waste heat. This seems like a good thing in the freezing cold of Pluto, but it is actually a trap. A reactor runs at hundreds of degrees. The electronics and the crew need to be at room temperature. You have to move that heat. You need radiators. But radiators work by glowing by emitting infrared light into space. In the inner solar system, radiators are efficient. At Pluto, the environment is cold, which helps, but the physics of radiating heat in a vacuum are slow. You need massive surface areas. Giant fins sticking out of the ship, glowing dull red in the infrared spectrum. These fins are fragile. They are vulnerable to micrometeoroid strikes. If a pebble the size of a grain of sand hits a radiator loop traveling at 10 miles per second, it punches a hole. The coolant leaks out. The reactor overheats. The system scrams automatically shuts down to prevent a meltdown. Suddenly the ship goes dark. The reactor is dead. The batteries have a few hours of charge. The temperature outside is minus 390 degrees Fahrenheit. The crew is now in a race against thermodynamics. The ship begins to cool. First, the water in the recycling pipes freezes, bursting the titanium lines. Then, the air begins to get cold. The humidity in the cabin condenses on the walls and turns to frost. The crew huddles in their sleeping bags, but the cold is relentless. It seeps through the insulation. It sucks the heat out of their bodies. Without the reactor, they cannot restart the engines. They cannot call Earth. They are a silent tomb, drifting past the orbit of Neptune. This fragility is why we have never sent humans beyond the moon. In low Earth orbit, if the power fails, you come home in an hour. On the moon, you can survive on batteries for 3 days. On the way to Pluto, you are walking a tightrope over a 20-year abyss. You need a power source that is perfect, one that never fails, never leaks, never breaks, for 2 decades. Humanity has never built a machine that complex that runs perfectly for that long without maintenance, and you cannot do maintenance on a nuclear reactor core while you are flying in space. You cannot just open the hood and change the spark plugs on a uranium fuel rod. This energy poverty defines every aspect of the ship's design. It dictates how much water the crew can use to wash. It dictates how warm the cabin can be. It creates a culture of scarcity. Every watt is measured. If someone wants to turn on a reading light, they are spending a resource that is finite. The crew lives in a constant state of energy anxiety, watching the gauges, knowing that their life is a byproduct of a controlled nuclear reaction that must not stop. And we haven't even talked about the fuel to move the ship yet. We are just talking about the power to sit still and breathe. The propulsion problem is a separate beast, a monster of mass and velocity that makes the life support problem look simple. Because to get to Pluto in a human lifetime, you have to go fast. And to go fast, you have to burn something. But what? Chemical rockets are too weak. Ion engines are too slow. We are trapped in the middle, needing a Goldilocks engine that gives us the thrust of a rocket with the efficiency of a sail. Such an engine exists in science fiction. In reality, it is a mess of theoretical physics and engineering roadblocks. The darkness of the Kuiper Belt is not just an absence of light. It is an absence of possibilities. Near Earth, we have options. We have solar power. We have gravity assists. We have rescue missions. Out there, the variables are stripped away until only one remains: mass. How much mass did you bring? How much energy is stored in that mass? If the answer is not enough, the equation balances itself by ending your life. As we visualize this lonely ship, a tiny spark of warmth moving through a cathedral of ice, we have to ask ourselves, is it fair to send people into that? Is it exploration, or is it a sacrifice? The silence of the radio lag, the invisibility of Earth, the dim gray light of the distant sun, it all adds up to an environment that is fundamentally hostile to human psychology and biology. We are creatures of the sun. We are children of the light. Taking us 3 billion miles away from our parent star is an act of violence against our nature. But let's assume we solve the power. Let's assume we build the perfect reactor. Let's assume the crew is psychologically made of steel. We still have to move the ship. We have to cross the ocean. And the currents of this ocean are made of gravity and delta, V. In the next stage of our analysis, we will open the hood of the propulsion systems. We will look at the rockets we have, the rockets we want, and the rockets we dream of, and we will see why even the most powerful engines in human history might just be firecrackers in the face of the void. The tyranny of the rocket equation is waiting for us. If you are beginning to feel the chill of the outer system, if the silence is starting to settle in, make sure you are subscribed. We are going to throttle up in the next part, and the G, forces might just crush the last of our optimism. Stay with me. The journey is only getting harder. The universe has a speed limit, which is light, but it also has a toll booth, and the currency it demands is momentum. When we dream of Pluto, we dream of the destination, the silent, nitrogen-covered plains, the jagged ice mountains, the stark beauty of a world frozen in time. We rarely dream of the journey because the journey is a nightmare of mathematics. It is a prison built not of bars, but of mass ratios. To understand why a human boot will likely never crunch into the surface of that dwarf planet, we must confront the most ruthless dictator in physics, the rocket equation. This equation, first derived by a Russian schoolteacher named Konstantin Tsiolkovsky in a log cabin in 1903, governs every movement we make in the void. It is elegant, simple, and absolutely unforgiving. It states a fundamental truth to move forward. You must leave something behind. A rocket is a machine that throws mass away. It explodes gas out of a nozzle at high speed, and the reaction pushes the ship in the opposite direction. It is Newton's third law written in fire. But here is the trap. The fuel you need to burn later, the fuel you need to slow down at Pluto, or to come home has weight. It has mass. To get that future fuel off the ground on Earth, you need more fuel to lift it. But that fuel also has mass, so you need even more fuel to lift the fuel that lifts the fuel. The relationship is not linear. It is exponential. It is a runaway train. To go twice as fast, you do not need twice the fuel. You might need 10 times the fuel. To go 3 times as fast, you might need 100 times. For a trip to the moon, the equation is manageable. The moon is close. We can use a massive rocket like the Saturn V, which was essentially a skyscraper filled with kerosene and liquid oxygen, to throw a tiny capsule to the lunar surface. The mass of the fuel was immense, but the trip was short. For Mars, the equation gets harder, but it is still solvable. We can send rovers. We can send humans, theoretically, if we accept a 6-month cruise and a massive ship. But Pluto is different. Pluto breaks the scale. To reach Pluto in a human lifetime, let's say, 20 years, you have to travel fast. You have to scream across the solar system at speeds that make Apollo look like a crawling insect. But the faster you go, the harder it is to stop. And this is the part that kills the mission design, the capture burn. New Horizons flew past Pluto at 1,000 miles per hour. It was a bullet. It had no intention of stopping. It didn't carry the fuel to stop. If it had tried to fire its thrusters to enter orbit, it would have been like a mosquito trying to stop a freight train. To stop a human ship at Pluto, to settle into a gentle orbit so we can descend to the surface, requires canceling out all that speed. We have to shed 30,000 miles per hour of velocity. To do that, we need a massive engine burn at the destination. That means we have to carry the fuel for that burn all the way from Earth. We have to lug millions of pounds of propellant across 3 billion miles of emptiness just to use it at the very end. And because of the rocket equation, carrying that fuel requires a launch vehicle on Earth that defies imagination. If we used conventional chemical rockets, the hydrogen and oxygen engines that power the Space Shuttle or the SLS, to send a fully equipped human habitat to Pluto and stop there, the ship waiting on the launch pad would not look like a rocket. It would look like a mountain. It would need to be the size of the Burj Khalifa, filled entirely with unstable cryogenic fuel, just to deliver a tiny cramped capsule to the edge of the system. And if you want to bring the crew back, if you want a round trip, the mountain becomes a mountain range. The mass required creates a paradox. The ship becomes too heavy to launch because of the fuel it needs to land. This is the chemical limit. We are addicted to fire. For all of human history, from the first campfire to the Raptor engine, we have created energy by breaking chemical bonds. We mix a fuel and an oxidizer, we add a spark, and the bonds snap, releasing heat. But chemical bonds are weak. The energy stored in the electron shells of an atom is finite. Even the most potent chemical reaction known to science, burning liquid hydrogen with liquid fluorine, releases a pathetic amount of energy compared to the distances of space. We are trying to cross an ocean in a rowboat, and we are burning the oars to keep warm. So, the engineers say, abandon chemistry. They look to the atom itself. They look to nuclear thermal propulsion. In this design, we don't burn the fuel. We use a nuclear reactor to heat hydrogen gas until it screams out of the nozzle at incredible speeds. It is twice as efficient as a chemical rocket. It gives us double the gas mileage. But double is not enough. The distance to Pluto is not double the distance to Mars, it is 20 times the distance. Even with nuclear rockets, the travel time is measured in decades. And nuclear engines have a fatal flaw for a mission this long: the hydrogen. To run a nuclear rocket, you need liquid hydrogen. It is the lightest element, the most efficient propellant. But hydrogen hates to be a liquid. It boils at minus 420, 3 degrees Fahrenheit. It is desperate to turn into a gas and expand. On a journey of 10 or 20 years, keeping that hydrogen liquid is a battle against thermodynamics. Heat from the sun, heat from the ship's own electronics, heat from the cosmic background, it all seeps into the tanks. The hydrogen warms up, it expands, the pressure rises. To prevent the tank from exploding, you have to vent the gas. You have to open a valve and let the precious fuel bleed away into space. This is called boil off. Over a decade, long coast to Pluto, a ship might lose half its fuel just to evaporation. You arrive at your destination, ready to fire the engine to stop, and you find the tanks are empty. The engine is dead. The ship sails past Pluto, the crew watching helplessly as their destination fades into the star field, unable to slow down, drifting forever into the interstellar void. To stop the boil off, you need active cooling. You need refrigerators, cryocoolers running 24 hours a day to keep the fuel sub zero. But refrigerators need power, massive amounts of power. Now you need a bigger reactor to run the refrigerators. The bigger reactor is heavier. The heavier reactor needs more fuel to move. The rocket equation laughs at you. It tightens the noose. Every solution creates a new problem that adds mass. And we haven't even discussed the reliability of the burn. Imagine the crew has survived the 20-year cruise. They are old now. They have spent a third of their lives in a metal box. They are approaching Pluto. The navigation computer wakes up. It calculates the precise second for the braking maneuver. The engine must fire for 45 minutes at full power to capture into orbit. This engine has sat cold and dormant for 20 years. The valves have been frozen. The lubricants have been exposed to vacuum. The seals have been bombarded by cosmic radiation. The computer sends the signal ignite. If that engine does not light, the mission is over. There is no second chance. The physics of a flyby are brutal. At 30,000 miles per hour, you cross the entire diameter of the Pluto system in a few hours. If the engine coughs, if a pump fails, if a valve sticks, the ship shoots past. The crew would have a front row seat to their own failure. They would see Pluto swell in the window, a majestic mottled ball of brown and white, and then they would see it shrink. They would recede into the darkness, moving too fast to ever turn around, bound for the empty space between the stars, where the temperature drops to absolute zero and the sun is just another star. The margin for error is zero. And human engineering is never zero, defect. We build machines that break. We build cars that don't start on cold mornings. We build phones that crash. Relying on a single mechanical system to work perfectly after 20 years of dormancy is a gamble that no space agency would ever sanction. So you need redundancy. You need backup engines, backup valves, backup computers, more mass, more fuel. The tyranny continues. There is a seduction in the idea of advanced propulsion. We hear about ion drives, the glowing blue engines of Star Wars and The Martian. In reality, ion thrusters are real. They are incredibly efficient. They use electricity to strip electrons from xenon gas and shoot them out the back. They are 10 times more efficient than chemical rockets. They don't gulp fuel, they sip it. But ion engines have no thrust. They are weak. A large ion engine produces about the same force as the weight of a coin resting on your hand. They can push a ship, but they have to push for years to build up speed. They are the tortoises of the galaxy. To move a massive human ship to Pluto using ion drives, you would need to spiral out slowly. It would take years just to leave Earth orbit. The travel time balloons from 20 years to 30, 40, maybe 50. And ion engines are hungry. They need electricity, massive amounts of it. To drive a human ship, you would need megawatt, class power supplies. Again, we are back to the nuclear reactor, the heavy, hot, radiation-spewing heart of the ship. We are trading chemical mass for nuclear mass and electrical complexity. The energy ledger never balances in our favor. Some dreamers look to the solar sail. They imagine giant mirrors, miles wide, catching the pressure of sunlight like a ship catching the trade winds. It is a beautiful image. A silent, shimmering clipper ship of the stars, requiring no fuel, driven by the pure light of the sun. But the inverse square law destroys this dream too. Solar pressure is weak near Earth. At Pluto, it is non-existent. The sun is too dim to push a sail. A solar sail works for the first leg of the journey, maybe getting you to Jupiter. But after that, the wind dies. You are becalmed in the dark, and a sail cannot stop you. To stop at Pluto, you would need a laser from Earth to push against the front of the sail, or the sun's light from the other side, but the sun is behind you. You would go hurtling past your target, a majestic silver ghost ship, unable to drop anchor. We are left with the uncomfortable realization that our current physics offers no good options. We are trapped in a low-energy valley. Chemical rockets are too inefficient. Nuclear rockets are too heavy and complex. Ion drives are too weak. Solar sails are useless in the dark. The mission to Pluto is not a problem of tweaking the variables. It is a problem of missing variables entirely. We need something else. We need a way to cheat the equation. Science fiction gives us warp drive, or wormholes, or antimatter. Antimatter is the holy grail. When matter meets antimatter, it annihilates completely, turning 100 of its mass into pure energy. It is the ultimate fuel. A few grams of antimatter could power a ship to Pluto in weeks. But we do not have antimatter. We can make it atom by atom in giant particle accelerators like the Large Hadron Collider. But the cost is astronomical. To make 1 gram of antimatter with current technology would cost trillions of dollars and take millions of years. The total amount of antimatter created in the history of the human race would not even light a light bulb for a few minutes. It is a fantasy fuel. It exists in equations, not in tanks. So we return to the cold reality. The ship sits on the pad in our minds. It is enormous. It is dangerous. It is filled with a crew who knows that they are likely embarking on a one-way trip into solitude. They know the math. They know the rocket equation is waiting for them in the dark, watching their fuel gauges, waiting for the moment when the needle touches zero. This is the barrier. It is not a wall of stone, but a wall of energy. Gravity is a well, and we are at the bottom of it. To climb out, to traverse the flat plane of the solar system, and to climb back down into the gravity well of Pluto requires a toll we cannot pay. But let's assume for a moment that we solve the propulsion. Let's assume we find a magic engine. Let's assume we get the crew to Pluto in 10 years. We still have to keep them alive. And the biological reality of the human body is even more fragile than the engineering of the rocket. In the deep space environment, the human body begins to dismantle itself. The fluids shift, the eyes distort, the DNA unspools. We are entering the biological phase of our analysis. The machine is hard to build, but the passenger is impossible to maintain. In the next chapter of this journey, we will step inside the hull. We will look at the air, the water, the radiation, and the slow decay of the human form in the absence of Earth. If you thought the rocket science was bleak, wait until you hear what the void does to the blood in your veins. If you are finding peace in the vast, unyielding limits of our reality, if the impossibility of the journey is helping you let go of your own daily struggles, make sure you are subscribed. There is a strange comfort in knowing that some things are simply beyond our reach. Let us drift further into the dark together. The next leg of the trip is internal. We often think of spacecraft as machines made of metal, silicon, and composite fibers. We obsess over the engines, the navigation computers, and the heat shields. But in a crewed mission to Pluto, the most complex, fragile, and dangerous component of the entire system is not the rocket. It is the cargo. It is the human body. A human being is a biological fire that must be fed constantly. We are engines of combustion. We take in oxygen and fuel, and we exhaust carbon dioxide, heat, and wastewater. On Earth, the biosphere handles this exchange for us for free. The trees scrub the air, the rain cycles the water, the soil processes the waste. We live in a massive, self-correcting life support system that we largely take for granted. But when you seal 6 human beings inside a metal pressure vessel and throw them into the vacuum for 20 years, you are removing them from that biosphere. You have to recreate Earth inside a box the size of a small house, and you have to do it perfectly. If the system is 99% efficient, the 1% of failure will accumulate over 2 decades and kill everyone on board. This is the entropy of breath. This is the tyranny of the water cycle, and it creates a mass penalty that rivals the fuel for the engines. Let us begin with the air. A human being at rest breathes about 12 times a minute. In those breaths, you consume roughly 500 liters of oxygen every single day. For a crew of 6, that is 3,000 liters of oxygen every 24 hours. Over the course of a 20-year mission to Pluto and back, that totals nearly 22 million liters of oxygen. If you were to store that oxygen in tanks, like scuba divers, the tanks alone would weigh hundreds of tons. The pressure vessels required to hold that much gas at high density would be so heavy that no rocket could lift them. The mass of the breathing gas would exceed the mass of the ship itself. So, you cannot bring all your air with you. You have to recycle it. You have to take the carbon dioxide that the astronauts exhale, which is a deadly poison in high concentrations, and chemically rip the carbon atom off the oxygen atoms, then feed the oxygen back to the crew. On the International Space Station, we do this with a machine called the Carbon Dioxide Removal Assembly. It uses beds of zeolite crystals to trap the CO2 molecules. Then we use a Sabatier reactor to mix that CO2 with hydrogen to produce water and methane. We split the water back into hydrogen and oxygen through electrolysis, and we vent the methane into space. It sounds elegant. It sounds like a closed loop, but it is not. The Sabatier process is not 100% efficient. It loses hydrogen. It loses oxygen. The zeolite beds degrade. The valves stick. On the space station, when the oxygen generator breaks, and it does break, we just wait for a cargo ship to bring a new one. Or we use backup candles that burn to produce oxygen. Or we vent the bad air and replace it with fresh air from tanks brought up from Earth. The station is not a closed system. It is a house with a window we can open and a delivery truck that comes every few months. On the way to Pluto, there are no delivery trucks. There are no replacement parts. There is no fresh air. If the oxygen recycling system drops from 95% efficiency to 90% efficiency, the crew will slowly suffocate. The oxygen levels will creep down day by day, year by year. It would be a slow hypoxia. First, their thinking would get fuzzy. They would make mistakes. Then, they would feel tired all the time. Their fingertips would turn blue. And finally, they would just go to sleep and never wake up. To prevent this, you need redundancy. You need 3 oxygen generators. You need spare parts for every pump, every fan, every sensor. All of those spares add mass. All of that mass fights the rocket equation. And then there is the water. The human body is essentially a walking sack of water. We are 70% fluid. We lose water constantly through sweat, through urine, through the moisture in our breath. A single astronaut needs about 3 to 4 liters of water a day for drinking and rehydration of food. For hygiene washing bodies and clothes, you need much more. On Earth, we use water once and throw it away. In space, every drop of water must be captured, purified, and drunk again. Coffee becomes urine. Urine becomes water. Water becomes coffee. The cycle is endless. On a 20-year mission, the crew will drink the same water thousands of times. They will drink the sweat of their crewmates. They will drink the condensation scraped off the cooling coils of the air conditioner. The psychological barrier to this is high, but the engineering barrier is higher. Water is heavy. 1 liter of water weighs 1 kilogram. To bring enough water for a use-once system for 6 people for 20 years would require nearly 200 tons of water. That is the weight of a blue whale. Launching a blue whale to Pluto is impossible. So, the water recovery system must be perfect. It must spin the urine in a centrifuge to separate the solids. It must distill the liquid. It must pass it through filters that catch bacteria, viruses, and heavy metals. It must check the pH balance. It must add iodine to kill any remaining microbes. And it must do this every single day, without fail, for 7,300 days. Filters clog, membranes tear, pumps seize. In the microgravity environment, water behaves strangely. It forms sticky globs that cling to surfaces. It doesn't flow downhill because there is no downhill. It hides in corners where mold can grow. If a biofilm of bacteria takes hold inside the pipes of the water recycler, it can poison the entire supply. The crew would be drinking sickness, and at 3 billion miles from the nearest doctor, a dysentery outbreak is a fatal event. Dehydration kills in days. But the most insidious enemy of the life support system is not the water or the air itself. It is the trace contaminants. Humans are filthy creatures. We shed dead skin cells constantly, billions of them a day. We fart, we burp, we sweat oils, we gas volatile organic compounds from our plastics and glues. We bring dust. In a house on Earth, you open a window and the wind blows it away. In a sealed spacecraft, there is nowhere for the filth to go. It accumulates. The skin cells float in the air until they are sucked into the intake vents of the computers. They clog the cooling fans. They coat the sensors. They become food for mold. The methane and sulfur from our digestion build up in the atmosphere. Without powerful scrubbers machines that use activated charcoal and catalytic oxidizers to burn these impurities, the air in the ship would become toxic within months. It would smell like a locker room, then like a sewer, and finally like a chemical plant. These scrubbers are consumables. Charcoal filters get full. They stop working. You have to throw them away and put in new ones. For a 20-year mission, you would need a warehouse full of filters. Where do you put them? Where do you store the used ones? You can't just toss them out the airlock, or you impart a tiny thrust to the ship that throws off your navigation. So you have to keep the trash. The ship slowly fills up with its own waste-used filters, dried fecal matter, broken parts. You are living inside a growing landfill, and we haven't even discussed the thermal control of the biologicals. Humans are very narrow in our thermal tolerance. If the temperature drops below 60 degrees Fahrenheit, we get clumsy and slow. If it rises above 80, we sweat and lose water too fast. The ship has to maintain a shirt, sleeve environment. This requires massive heaters because outside is absolute zero. But it also requires cooling, because inside, the bodies of the astronauts are generating heat. 6 people generate about 600 watts of heat just by being alive. If they exercise, which they must, to keep their bones from dissolving, they generate thousands of watts. The life support system has to move this heat around. It uses fluid loops pipes filled with ammonia or water to collect the heat from the cabin and move it to the radiators outside. These pumps must never stop. If the thermal loop fails, the temperature in the ship will skyrocket or plummet within hours. The astronauts would be either boiled in their own sweat or frozen in their bunks. Complexity is the enemy of reliability. The more moving parts you have, the more likely something is to break. A toilet on Earth is a simple ceramic bowl with gravity to do the work. A toilet in space is a $10 million machine with suction fans, separators, acid tanks, and vacuum sealers. It breaks all the time. On the space station, toilet repair is a regular duty. It is messy, unpleasant, and critical. Imagine doing that for 20 years. Imagine the spare parts running out in year 15. What do? You cannot improvise a high-pressure vacuum pump out of duct tape. The Biosphere 2 experiment in the 1990s tried to seal 8 people inside a 3-acre glass terrarium in Arizona. They had a rainforest, an ocean, a farm, and breathable air. Within months, the oxygen levels crashed. The concrete walls were absorbing the CO2. The pollinators died. The crops failed. The crew began to starve and suffocate. They had to pump in fresh air from the outside. That was on Earth. with sunlight and gravity. We have never, ever built a truly closed-loop life support system that worked for years without external help. We are betting the lives of the Pluto crew on technology that does not exist in a mature state. This leads to the mass spiral again. To be safe, you need redundancy. You need 3 toilets, 4 water recyclers, 5 tons of spare filters, 10 tons of oxygen candles. The mass of the safety margin becomes heavier than the crew, and every kilogram of that safety margin requires 10, 20, or 50 kilograms of fuel to push it to Pluto. We are aquatic, aerobic organisms evolved for a planet with a thick atmosphere and a magnetic field. We are soft. We are wet. We are chemically unstable. Trying to keep a human body alive in the deep vacuum is like trying to keep a flame burning underwater. You can do it with enough technology, but the moment the technology falters, the ocean rushes in. The comparison to submarines is often made, but it is a false comfort. A nuclear submarine can stay underwater for 3 months. It makes its own air and water, but it has an unlimited supply of cooling water right outside the hull. It has gravity. And most importantly, if the reactor scrams, if the air goes bad, the captain blows the ballast tanks and surfaces. Within minutes, the hatch is open and fresh Pacific air rushes in. At Pluto, surfacing is impossible. You are submerged in an ocean of nothingness that is billions of miles deep. There is no up. There is only out. The psychological toll of this dependence on machinery cannot be overstated. The crew knows that every breath they take is a gift from a machine. They know that the water in their pouch was urine yesterday. They know that the hum of the ventilation fans is the sound of their own survival. If that hum stops, the silence that follows is the sound of death. This creates a vigilance. You listen to the ship. You obsess over the readouts. You stop trusting the air. This anxiety burns calories. It increases metabolic rate. It consumes more oxygen. The fear itself becomes a drain on the consumables. And what happens when the biology itself fails? We are not just machines, we are ecosystems. We carry bacteria in our gut that digest our food. We carry viruses in our DNA. In the stress of spaceflight, the human immune system weakens. Latent viruses like herpes or chickenpox can reactivate. The bacteria in our gut can change, becoming more virulent. An infection that would be a minor annoyance on Earth becomes a crisis in a closed environment. A common cold could sweep through the crew and, with no fresh air to flush it out, linger for months, mutating and re-infecting them. Medical care requires supplies. Antibiotics have a shelf life. They degrade. After 10 years, the pills in the medical kit might be useless powder. If an astronaut gets an infection in year 12 and the drugs have turned to dust, they die from a cut on their finger, just like a medieval peasant. To prevent this, you need a refrigerator for the drugs. More power, more mass. You need the ability to manufacture medicines on board, a chemistry lab, more mass. The entropy of the biological system is relentless. The ship starts pristine, clean, and full of supplies. Day by day, it degrades. The filters fill up. The water gets a little more brackish. The air gets a little more stale. The walls get coated in a microscopic layer of grime. The spare parts bin gets emptier. The crew gets older. Their cells accumulate radiation damage. Their bones get thinner. It is a slow, grinding war of attrition against the laws of thermodynamics. We want to believe that we can engineer our way out of this. We want to believe that we can build a ship that is a perfect, eternal garden, but we cannot even do that on Earth. We cannot build a car that runs for 20 years without a mechanic. We cannot build a house that doesn't leak. To expect a spacecraft to function as a perfect, self-sustaining biosphere for 2 decades is to expect a miracle. And physics does not grant miracles. It only grants consequences. The oxygen you breathe on Pluto will be the most expensive substance in the history of the solar system. Every molecule of it has to be carried, scrubbed, monitored, and fought for. And if the machine stops, even for a few hours, the journey ends not with a bang, but with a gasp. But air and water are only the immediate needs. A human being can survive 3 minutes without air and 3 days without water. We can survive 3 weeks without food. But for a 20-year mission, the hunger is a different kind of beast. It is not just about calories, it is about the slow decay of the nutrients themselves. In the next section, we will open the pantry. We will look at the 79 tons of food required for the voyage, and we will discover why a crew might starve to death with a full stomach. The biology of deep space is about to get even more complicated. If you are beginning to appreciate the sheer weight of your own breath, if you are looking at your glass of water with a new respect for the cycle that brought it to you, make sure you are subscribed. We are going to dig into the caloric nightmare of the Pluto run next. The menu is set, and it is not appetizing. On Earth, hunger is a signal. It tells you to open the refrigerator, visit the market, or harvest a crop. It is a temporary discomfort solved by a complex, global infrastructure of agriculture and logistics. But on a spacecraft bound for the edge of the solar system, hunger is a mathematical inevitability that must be solved before the launch button is ever pressed. You cannot stop at a drive through near Jupiter. You cannot resupply. You have to pack every single calorie, every gram of protein, and every molecule of fat that 6 human beings will consume for 20 years. The sheer mass of this pantry is difficult to visualize. An active astronaut needs roughly 2,500 to 3,000 calories a day to maintain body mass in a high-stress environment. That translates to about 4 pounds of food per person per day, including packaging. For a crew of 6, that is 24 pounds of food every morning. Over a year, that is nearly 9,000 pounds. Over a 20-year mission, the total comes to approximately 175,000 pounds. That is roughly 80 metric tons. 80 tons of food. That is the weight of a space shuttle orbiter, just for the lunch boxes. To launch 80 tons of lasagna and freeze dried strawberries to Pluto requires a rocket larger than anything humanity has ever built. But the mass is only the first problem. The second problem is time. We do not have food technology that lasts for 20 years. Go to your pantry and look at a can of beans. The expiration date is probably 2 or 3 years from now. Military MRE's meals ready to eat are designed to last 5 years in climate-controlled warehouses. After 5 years, the taste degrades. The texture turns to mush. The oils separate and go rancid. But taste is a luxury. The real killer is nutritional decay. Vitamins are complex, fragile organic molecules. They are held together by chemical bonds that are sensitive to heat, radiation, and oxidation. Over time, even in a sealed, dark pouch, these bonds break. Vitamin C, ascorbic acid, is particularly unstable. It reacts with trace amounts of oxygen. It breaks down into compounds that provide no nutritional value. Vitamin B1, thiamine, is also sensitive. Imagine the crew in year 7 of the mission. They are still eating the food packed on Earth. The pouches are sealed. The calories are there. They feel full after eating, but their bodies are starving. Without vitamin C, the collagen in their bodies stops forming correctly. Old scars from childhood begin to open up. Their gums bleed, their teeth loosen. They develop scurvy, the ancient scourge of sailors who crossed the oceans without fresh fruit. It is a cruel irony traveling in the most advanced machine ever built, powered by nuclear reactors, yet dying of a disease from the 17th century because the vitamins in your food have turned to dust. To prevent this, you would need to fortify the food with massive overdoses of vitamins, hoping some survive. Or you would need to synthesize vitamins on board, a chemistry lab, a pharmacy. More mass, more complexity. The optimists say, we will grow food. They point to the International Space Station where astronauts have grown lettuce and radishes. They imagine a greenhouse on the ship, a lush garden providing fresh tomatoes and oxygen. It is a beautiful image. It is also an energy nightmare. Plants are incredibly inefficient solar collectors. They convert a tiny fraction of light energy into chemical energy. To grow enough food to feed 6 people, not just a salad once a week, but a full caloric diet of wheat, soy, and potatoes, you would need acres of growing surface. At Pluto, there is no sunlight. You would need to light these acres with LEDs. The power requirement for that lighting would be in the megawatts. You would need a nuclear reactor just to run the grow lights. And plants are fragile. They get sick. A single spore of wheat rust or a mold infestation could wipe out the entire crop in weeks. If the farm dies in year 10, the crew dies in year 11. So, you cannot rely on the farm. You have to bring the 80 tons of preserved food anyway. The farm becomes a hobby, a psychological crutch, not a life support system. The energy budget simply does not allow for a self-sustaining ecosystem, so the crew eats their paste. They eat their gray, vitamin, fortified sludge for 7,300 days. The psychological impact of this culinary monotony is profound. Food is comfort. Food is culture. Denying it for decades creates a stress that gnaws at the mind. But while the crew is fighting the internal battle of hunger and nutrition, a silent, invisible storm is raging outside the hull. Radiation. Space is not empty. It is filled with subatomic particles moving at nearly the speed of light. There are two main sources. The sun throws out protons and electrons in the solar wind. These are dangerous, but they are relatively low energy. We can shield against them with a few inches of aluminum or water. The real threat comes from the deep, dark galactic cosmic rays. These are heavy ions, iron nuclei, gold nuclei stripped of their electrons and accelerated by supernova explosions millions of years ago. They are bullets the size of atoms, but they carry the kinetic energy of a baseball moving at 90 miles per hour. When a galactic cosmic ray hits a spacecraft, it does not just bounce off. It smashes through the hull like a cannonball through smoke. It shatters the metal atoms, creating a spray of secondary radiation, a shotgun blast of neutrons and X-rays inside the ship. When these particles hit human flesh, they tear through the cells. They break the double helix of the DNA. The body has repair mechanisms to fix DNA, but GCRs cause complex double-strand breaks that are hard to repair. The code gets scrambled. Cells die, or worse, they mutate. They become cancerous. On a trip to the moon, you are only exposed for a few days. On the space station, the Earth's magnetic field protects you from most of this. But on the way to Pluto, you are naked. You are out in the open ocean of the galaxy. Over 20 years, the cumulative dose of radiation would be catastrophic. It would destroy the crew's bone marrow. It would cloud the lenses of their lenses, causing cataracts. It would turn their brains into Swiss cheese, degrading cognitive function. The crew would arrive at Pluto not as explorers, but as dementia patients riddled with tumors. To stop GCRs, you need mass. You need hydrogen. Hydrogen is the best shield because it has a similar mass to the incoming protons, so it scatters them effectively. Water is rich in hydrogen. Polyethylene plastic is rich in hydrogen. So the best design for a Pluto ship is to surround the crew quarters with a jacket of water, a storm shelter. But we already established that water is heavy. To build a shelter thick enough to block high, energy cosmic rays, perhaps 2 or 3 meters of water thickness around the entire habitat, you are adding hundreds of tons of mass. The rocket equation returns to haunt us. The shield makes the ship too heavy to move. If you make the shield thinner to save weight, you kill the crew with radiation. If you make it thick enough to be safe, you can't launch. There is no magical force field like in Star Trek. Magnetic shielding is theoretically possible using giant superconducting magnets to deflect the particles, but the power required to run those magnets is, again, in the megawatts. And the magnets themselves are heavy. And if the cooling system for the magnets fails, the field collapses and the radiation floods in. The crew would live in a constant state of bombardment. Astronauts on Apollo reported seeing flashes of light when they closed their eyes. This was caused by cosmic rays passing through their eyelids and striking the retina directly, triggering a false signal in the optic nerve. On the way to Pluto, these flashes would be a nightly fireworks show, a constant reminder that invisible bullets are passing through your brain while you sleep. And finally, amidst the hunger and the radiation, there is the paradox of heat. We think of space as cold, and Pluto is cold, minus 390 degrees Fahrenheit. But a spacecraft is a thermos bottle. In the vacuum of space, heat cannot conduct away. It can only radiate. Inside the ship, you have 6 human bodies, each generating 100 watts of heat. You have computers, pumps, scrubbers, and lights, all generating heat. If you insulate the ship perfectly to keep out the cold of space, the heat inside builds up. The temperature rises. It hits 80 degrees, then 90, then 100. The crew cooks in their own body heat. So you need an active thermal control system. You need loops of fluid that pick up the heat from the cabin and carry it to radiators on the outside. These radiators glow in the infrared, dumping the waste heat into the blackness. But this system must be incredibly precise. If the ship turns its radiators toward the sun, even at Pluto's distance, they might absorb too much heat. If they turn away, they might freeze. The fluid in the pipes, usually ammonia, can freeze if the flow stops for even a minute. If the radiator fluid freezes, the pipes burst. The cooling loop dies. The heat inside the ship begins to climb uncontrollably. Or, conversely, if the reactor that powers the heaters fails, the ship plunges into the deep freeze. The thermal inertia of the ship would hold the heat for a few days, but eventually the walls would cool. The condensation from the crew's breath would turn to ice on the bulkheads. The water in the recycling system would freeze and expand, shattering the pipes. The air itself would begin to liquefy. The crew is trapped in a narrow thermal corridor. They are balancing on a knife's edge between being boiled and being frozen, and this balance requires constant energy. It requires pumps that never fail. It requires valves that never stick. It requires a computer that constantly adjusts the flow rates to match the metabolic Ausgangsfout of the crew. Imagine the sound of those pumps, a low, thrumming vibration in the walls. It is the heartbeat of the ship. If it stops, you die. If it speeds up, you worry. If it makes a new noise, you panic. For 20 years, that sound is the only thing standing between you and the temperature of the void. We have built machines that last 20 years, the Voyagers, the pioneers. But they are simple. They are robot skeletons. They do not have to keep blood liquid and air breathable. They do not have to shield DNA from heavy ions. They do not have to keep 79 tons of food from rotting. When you add it all up, the food, the water, the air, the radiation shielding, the thermal control, the mass of the life support system becomes the dominant factor in the mission. It dwarfs the scientific equipment. It dwarfs the crew. The ship is essentially a giant flying hotel that must be fortified like a bunker and powered like a city. And remember, we have to push all of this mass to Pluto. We have to accelerate it to 30,000 miles per hour. The energy required to move the hotel is thousands of times greater than the energy required to move a probe. This is the great filter of human exploration. It is not that we are not smart enough. It is that we are too heavy, too hungry, and too fragile. We are trying to force a biological organism that evolved for a warm, wet, thick atmosphere into an environment that is hostile to the very concept of biology. So, is it impossible? Or is there a way out? Is there a technology on the horizon that could change the equation? Could we hibernate? Could we freeze ourselves and wake up at the destination, bypassing the hunger and the boredom? Or could we build a ship that doesn't need to carry its fuel? In the next part of our analysis, we will look at the cheat codes. We will examine the concepts of cryosleep, fusion drive, and antimatter. We will ask if the future of physics can save us from the limitations of the present. But be warned, science fiction is often much kinder than science fact. The dream of sleeping through the journey might just be another nightmare in disguise. If you are feeling the weight of the pantry and the chill of the cosmic rays, take a moment to breathe the free, abundant air of Earth. Drink a glass of water that didn't come from a machine. And if you want to see how deep the rabbit hole goes, make sure you are subscribed. We are about to try and break the laws of physics. The ship we have been building in our minds, the vessel capable of keeping 6 human beings alive, warm, and fed for 20 years in the dark, is no longer a ship. It has become a monstrosity. We have added layers of radiation shielding made of water and polyethylene. We have added nuclear reactors for power and nuclear engines for propulsion. We have added warehouses of food, tanks of air, and recycling plants for water. We have added redundancies for every pump, every valve, and every computer. When we sum up the mass of all these requirements, we are not looking at a sleek rocket like the Saturn V. We are looking at something that weighs thousands of metric tons. This brings us to a logistical barrier that is just as formidable as the distance itself, gravity. Earth is a gravity well. To get anything into space, we have to fight the pull of the entire planet. We have to accelerate to 17,500 miles per hour just to stay in low Earth orbit. The energy cost of this initial step is staggering. To put 1 kilogram of payload into orbit using current technology costs thousands of dollars and burns hundreds of kilograms of rocket fuel. The ratio is brutal. For every pound of cargo you want in space, you need 20 to 50 pounds of rocket on the ground. Now apply this to our Pluto ship. Let us be conservative and estimate the dry mass of the ship, the structure, the shielding, the crew, the supplies, but not the fuel for the trip at 500 metric tons. That is roughly the mass of the entire International Space Station. But the ISS was not launched in one piece. It was launched in dozens of separate missions over more than a decade. It was assembled by astronauts doing spacewalks, bolting modules together, connecting wires, and sealing hatches. For a Pluto mission, we would have to do the same thing. We would have to launch the nuclear reactor on one rocket, the crew habitat on another, the fuel tanks on a third, fourth, and fifth, the engines on a sixth. We would need a fleet of heavy, lift-launch vehicles, starships, SLS blocks, or New Glens flying a continuous cadence for years. This creates an energy debt before the mission even begins. The amount of kerosene, hydrogen, and methane burned in the Earth's atmosphere just to lift the components of the Pluto ship would be equivalent to the energy consumption of a small nation. We are burning the Earth to leave it. But the real problem is the assembly itself. Building a ship in space is not like building a ship in a shipyard. On Earth, if you drop a wrench, you pick it up. If a weld is imperfect, you grind it down and redo it. If a seal leaks, you replace it. In orbit, every task is a life-threatening operation. The astronauts building the ship are working in pressurized suits that are stiff and clumsy. They are working in a vacuum where temperatures swing from boiling to freezing every 90 minutes as they orbit the Earth. Imagine connecting the cooling pipes for a megawatt-class nuclear reactor while wearing oven mitts, floating in zero gravity, knowing that a single microscopic leak in a weld could doom the mission 10 years later. The precision required is absolute. A connection that is 99.9 perfect is a failure. Over 20 years, that 0.1 imperfection will vibrate, expand, contract, and eventually crack. And when it cracks, it will be 3 billion miles away from the nearest repair crew. This introduces the concept of infant mortality in engineering. Complex systems tend to fail early, or they fail late. This is known as the bathtub curve. When you build a new machine, you expect bugs. You expect wires to cross, software to crash, and valves to stick. On Earth, you run sea trials. You sail the ship around the harbor for a few weeks to shake out the problems. But how do you sea trial a nuclear spaceship bound for Pluto? You cannot test the engines at full power in Earth orbit because the radiation would be dangerous, and the thrust would push the orbit out of alignment. You cannot test the life support system for 20 years because you don't have 20 years to wait. You have to launch the ship green. You have to trust that the thousands of connections made in the vacuum of space were perfect. You have to trust that the software has no hidden bugs that only appear after 10,000 hours of runtime. This trust is mathematically unsound. The Pluto ship would have millions of individual parts. Even if every part has a reliability of 99.999, the probability of the entire system functioning perfectly for 2 decades is near zero. Something will break. It is a statistical certainty. On the ISS, when a gyroscope fails, we tolerate it because we have 3 others. If the toilet breaks, we have 2. If the oxygen generator fails, we have tanks. But the Pluto ship cannot carry infinite spares. Every spare part adds mass. Every kilogram of mass requires more fuel. We are back in the loop. The safety margin is the mass that kills the mission performance, and then there is the entropy of the materials themselves. We think of metal and plastic as permanent, but in the harsh environment of deep space, they are not. They age. Consider the rubber seals. Every hatch, every valve, and every window on the spacecraft relies on an elastomer seal to keep the air in and the vacuum out. Over time, rubber dries out. It becomes brittle, it loses its elasticity. This is accelerated by radiation and thermal cycling. After 10 years, a seal that was flexible and tight becomes hard and cracked. It starts to leak, not a blowout, but a hiss. A slow, invisible loss of atmosphere. The crew would spend their days hunting for leaks. They would live in a ship that is slowly losing its integrity. The very walls of the habitat are under constant stress from the internal pressure of the air against the vacuum outside. Metal fatigue sets in. Cracks form in the aluminum or titanium structure. These cracks grow with every vibration of the pumps, every thermal creak of the hull. Electronics are even more vulnerable. We discussed radiation hitting DNA, but radiation also hits silicon. A single cosmic ray can flip a bit in a computer's memory, changing a 0 to a 1. This is called a single event upset. Modern spacecraft use radiation, hardened chips, which are slower and heavier, to resist this. But over 20 years, the cumulative dose degrades the silicon lattice itself. The transistors start to leak current. The voltages drift. The computer that navigates the ship in year 1 might be senile by year 15. Wiring insulation breaks down. In the oxygen-rich environment of a spacecraft, this is a fire hazard. The Apollo 1 fire taught us that materials' flammability changes in pure oxygen or pressurized environments. Over decades, the plastic coating on the miles of wire inside the walls becomes brittle. It flakes off. A bare wire touches a metal strut. A spark jumps. In the silence of deep space, a fire is the end. There is no running away. You cannot open a window to let the smoke out. You have to seal off the module, cut the power, and hope the fire suppresses itself. But now you have lost a section of your ship. You have lost equipment. The air is tainted with toxic smoke. The scrubbers have to work overtime to clean it, using up their filter life. This slow degradation of the machine creates a psychological environment of dread. The crew knows the ship is dying. They can hear it. The fans get louder as the bearings wear out. The pumps rattle. The displays flicker. They are living inside a mechanical organism that is terminally ill. They are the caretakers of a dying beast, trying to nurse it all the way to Pluto before it collapses. And we must address the fuel for the return trip. We have talked about getting there, but if we want the crew to come home, we have to carry the fuel for the return journey all the way to Pluto. This is the tyranny of the gear ratio. To bring 1 pound of payload back to Earth, you might need to land 10 pounds of fuel on Pluto. To land 10 pounds of fuel on Pluto, you might need to launch 100 pounds from Earth orbit. To launch 100 pounds from Earth orbit, you need thousands of pounds on the launch pad. This multiplier effect means that a round-trip mission is exponentially harder than a one-way trip. Most mission architectures for Mars assume we will make fuel on Mars. We call this in situ resource utilization. We would land a robot, suck carbon dioxide from the Martian air, mix it with hydrogen from the ice, and make methane fuel. But Pluto has no thick atmosphere. It has nitrogen and methane ice, yes, but mining it requires heavy equipment. You would need to land a drilling rig, a refinery, and a power plant on the surface of Pluto. You would need to operate this industrial complex remotely from orbit, or send the crew down to do it. But the crew has been in zero gravity for 10 years. Their bones are weak. Their muscles are atrophied. They cannot dig ditches in spacesuits. So you cannot refuel at Pluto. You have to bring everything. The ship that leaves Earth must be the ship that returns. This doubles, triples, quadruples the mass. It makes the ship so large that we simply do not have the launch capacity to build it. We would need a global effort, a Manhattan Project multiplied by the Apollo program, sustained for 20 years, just to assemble the vehicle. The economic energy required to do this, the sheer amount of human labor, raw materials, and political capital, is a resource that is just as finite as hydrogen. Societies lose interest, budgets get cut. A 20-year construction project in orbit is vulnerable to every election cycle, every recession, every war on Earth. If the funding stops in year 5 of assembly, the half-finished skeleton of the ship drifts in orbit. $1 trillion ruin. We have seen this before. The superconducting super collider in Texas, the Soviet N-1 rocket, Massive, ambitious projects that were canceled because they became too heavy, too expensive, or too complex. The Pluto mission is the ultimate megaproject. It requires a stability of human civilization that has rarely existed. So, the barrier is not just physics. It is the interaction between physics and the fragility of human institutions. The energy required to build the ship is so high that it destabilizes the economy that tries to build it. The complexity of the ship is so high that it exceeds our ability to verify its safety. The duration of the mission is so long that it exceeds the lifespan of the components that make up the ship. We are trying to bridge a gap that is too wide for our materials. We are carbon-based life forms who figured out how to burn dead plants to make steam. We have refined that technology, wrapped it in aluminum, and pointed it at the stars. But we are still, fundamentally, burning things to move. And burning things is a primitive way to travel. Until we discover a new physics, a way to manipulate gravity directly, or a way to extract energy from the vacuum itself, we are grounded by the weight of our own ambition. The rocket equation is a padlock on the solar system, and we do not have the key. In the next section, we will confront the false promise of the future. We will look at why we keep telling ourselves that technology will save us, and why that belief is a trap. We will examine the specific numbers of the energy budget for the entire mission and compare it to the outhench of our civilization. The final accounting is approaching, and the ledger is bleeding red ink. If you are fascinated by the sheer scale of the engineering challenges we face, and if the complexity of a simple seal in a vacuum makes you wonder how we ever leave the ground, make sure you are subscribed. We are building the final argument for why Pluto sleeps alone. We live in a civilization that has forgotten the difference between money and energy. We look at a problem like climate change, or poverty, or space travel, and we say, if only we had the budget. We assume that with enough dollars we can buy anything. But the universe does not accept dollars. It does not accept gold, or Bitcoin, or political promises. The universe only accepts joules. It creates a hard limit on what we can do, regardless of how rich we think we become. To understand why a human mission to Pluto is likely a fantasy, we have to stop looking at the price tag in dollars and start looking at the price tag in energy. We have to perform a thermodynamic audit of our own species. Let us begin with the fuel. We have established that chemical rockets are too weak and nuclear rockets are our only hope. To build a nuclear thermal rocket capable of pushing 500 tons to Pluto, we need uranium, 235. But uranium does not come out of the ground ready to use. Natural uranium is mostly U-238, which is useless for high-performance rockets. To get the U-235, the explosive, energy-dense isotope, we have to enrich it. Enrichment is one of the most energy-intensive industrial processes on Earth. We have to turn the uranium into a gas, uranium hexafluoride. Then we spin it in centrifuges at supersonic speeds. The heavier U-238 drifts to the outside. The lighter U-235 stays in the middle. We have to do this thousands of times in a cascade. The centrifuges consume massive amounts of electricity. They require entire power plants just to keep them spinning. To enrich enough uranium for a fleet of nuclear rockets, hundreds of kilograms of highly enriched weapons-grade material, we would need to dedicate a significant fraction of the world's enrichment capacity to the project for years. This is energy that cannot be used to light our cities, run our factories, or power our hospitals. It is energy we are withdrawing from the terrestrial economy to shoot into the void. And that is just the fuel for the reactor. What about the propellant, the hydrogen? We need tens of thousands of tons of liquid hydrogen. To make hydrogen, we usually strip it from natural gas, which releases CO2, or we split water using electricity electrolysis. Electrolysis is inefficient. Then, we have to cool that hydrogen to minus 423 degrees Fahrenheit to liquefy it. The liquefaction penalty is a thermodynamic tax. To make a gas into a liquid requires massive refrigeration compressors running 24/7. It takes roughly 10 to 13 kilowatt-hours of electricity to produce and liquefy 1 kilogram of hydrogen. For a mission requiring 50,000 tons of hydrogen, 50 million kilograms, the energy bill is in the hundreds of gigawatt-hours. That is the annual outhanch of a medium-sized power plant, just to make the gas for the tank. Then we have to launch it. The Earth is a gravity well. To lift 1 kilogram of that hydrogen into low Earth orbit, we have to burn 15 to 20 kilograms of rocket fuel in the first stage of the launch vehicle. We are burning fuel to move fuel. The energy return on energy invested (EROEI) for space travel is terrible. We are spending a fortune in energy to move a penny's worth of payload. When you sum up the energy to mine the ore, refine the metal, manufacture the high-tech alloys, enrich the uranium, liquefy the hydrogen, and launch the components, the total energy cost of a Pluto mission begins to rival the energy consumption of a small country. We are not talking about a mission anymore. We are talking about a civilization, level exertion, and this brings us to the opportunity cost. Energy is finite. If we spend 100 exajoules of energy on a Pluto mission, that is 100 exajoules we cannot spend on solving problems on Earth. We cannot use it to desalinate water for drought-stricken regions. We cannot use it to build seawalls against rising oceans. We cannot use it to scrub carbon from the atmosphere. The moral calculus of the mission shifts. Is it ethical to burn the equivalent of a nation's energy budget to send 6 people to a frozen rock 3 billion miles away, while billions of people on Earth are energy poor? This is not a political question, it is a resource distribution question. The false promise of futurity is the belief that we will always have more energy. That fusion is just around the corner, that solar panels will become 100 efficient. But history shows that technology follows an S-curve. It improves rapidly at first, then it plateaus. We saw this with airplanes. From 1903 to 1960, planes went from canvas gliders to supersonic jets. But since 1960, commercial jets have not gotten much faster. They have just become more efficient. We hit the barrier of the speed of sound and the efficiency of the jet engine. Rocket technology is on a similar plateau. The Raptor engine is a marvel, but it is not a quantum leap over the F1 engine of the Saturn V. It is a refinement. We are squeezing the last few percent of efficiency out of chemical combustion. We are near the top of the S-curve. We are not going to see a 100 times improvement in chemical rockets. It is physically impossible because of the energy density of the chemical bond. So we wait for the breakthrough. We wait for the warp drive, the epigenetic drive, the zero-point energy module. But waiting is a trap. This is the weight calculation paradox. If we launch a ship to Pluto today, using our best nuclear thermal rockets, it takes 30 years. Let's say we decide to wait 30 years for technology to improve. In 2055, we launch a better ship that takes 10 years. It arrives at the same time as the first ship would have. So, did we save anything? We saved the crew 20 years of travel, but we delayed the arrival by 30 years of waiting. But what if the breakthrough never comes? What if nuclear thermal propulsion is as good as it gets? What if fusion turns out to be impossible to miniaturize? Then we waited 30 years for nothing. The window of opportunity might close. Civilization might collapse. We might run out of the surplus energy required to launch anything. There is a terrifying possibility that we are currently living in the golden age of spaceflight potential, and we are wasting it. We have the fossil fuels to build the rockets. We have the nuclear material, but we are burning through our planetary battery at an alarming rate. A Pluto mission requires a surplus of energy that we might not have in 50 years. As oil becomes scarcer, as climate change forces us to spend energy on survival rather than exploration, the luxury of deep space travel will be the first thing to be cut. The false promise tells us that the future is Star Trek. The reality might be that the future is Mad Max. In a resource-constrained world, nobody builds a starship. They build walls. They build water purifiers. They build weapons. The Pluto mission requires a prosperous, stable, energy-rich, global civilization that can afford to throw a massive chunk of its wealth into the dark and expect nothing in return for 50 years. Who pays for this? A government? Governments operate on election cycles of 4 to 6 years. A Pluto mission spans 40 years, 20 years to build, 20 years to fly. That is 10 election cycles. 10 administrations. 10 chances for a new president or prime minister to say, "This is too expensive, cancel it." The superconducting supercollider was canceled after billions were spent. The Apollo program was canceled before we even built a moon base. The N-1 rocket was scrapped. To sustain political will for 40 years requires a monolithic culture, something like the pharaohs building the pyramids, or a totalitarian regime that does not care about public opinion. A democracy struggles to maintain focus on a multi-generational project that offers no immediate benefit to the voter. Why are we spending trillions on Pluto when my rent is too high? Is a question that kills space programs. And a corporation? Companies need profit. There is no profit on Pluto. There is no unobtainium. There is only nitrogen ice and water ice. We have water on Earth. We have nitrogen in the air. Mining Pluto is economic suicide. The cost of bringing a kilogram of gold back from Pluto would be millions of times the value of the gold itself. So, Elon Musk isn't going to Pluto. Jeff Bezos isn't going to Pluto. There is no business case. This leaves us with pure science, pure curiosity. And while curiosity is powerful, it has never commanded one of the global GDP. We spend pennies on NASA compared to the military or healthcare. To go to Pluto, we would need to invert our civilization's priorities. We would need to value knowing over comfort. We would need to value exploration over security. Humans are not wired that way. We are wired to protect the cave, feed the tribe, and conquer the neighbor. We are not wired to throw our harvest into the abyss to see what happens. This realization is the heavy anchor that drags the dream down. The physics are hard, the biology is brutal, but the economics are impossible. The energy accounting reveals that we are simply too small, too poor, and too divided to make the trip. We are a Type 0.7 civilization on the Kardashev scale. We harness the power of dead plants. To travel to the outer solar system, to truly inhabit it, we need to be a Type 1 civilization. We need to harness the full power of our planet, or the sun itself. We are children trying to build a skyscraper out of mud. The materials simply do not support the structure. There is a concept called the Great Filter. It suggests that there is a barrier that prevents civilizations from expanding into the galaxy. Maybe the filter is nuclear war. Maybe it is climate change. Or maybe, just maybe, the filter is the rocket equation itself. Maybe the energy cost of leaving a solar system is simply too high for any biological species to pay. Maybe the universe is designed to be an archipelago of isolated islands, where each civilization stays on its home rock, looks at the stars, dreams of crossing the ocean, but never builds a boat big enough to survive the waves. We look at the Voyager probes, drifting silent and dead in the interstellar medium, and we think they are the scouts for an invasion. But they might be the only things that ever leave. They might be our tombstones. Here lived a species that figured out how to throw a rock, but not how to follow it. The energy budget of the universe is vast. Stars burn with a fury that defies comprehension. But that energy is out there. Here, on Earth, we are fighting over scraps. And until we solve the energy problem here, until we have fusion, or vast orbital solar arrays, or some physics we haven't dreamt of, Pluto will remain a point of light. The ship we imagined, the nuclear, powered, water, shielded, spinning, gravity, hydroponic, farming Leviathan, is a ghost ship. It exists only in our renderings. It cannot be built because the energy to build it does not exist in a form we can use. The numbers don't lie. The equation balances at 0. In the final part of our journey, we will bring all these threads together. We will look at the destination one last time. We will synthesize the distance, the cold, the radiation, the biology, and the energy into a final conclusion about our place in the cosmos. We will ask, if we can't go to Pluto, what does that mean for our future? Are we trapped? Or is there another way to look at the limit? If you are ready to face the final curtain, to accept the boundaries of our existence, make sure you are subscribed. The end of the journey is in sight, and it is a quiet, frozen place. Stay with me for the conclusion. We have arrived at the final accounting. Tracing the journey from the launch pad to the edge of the system, we found toll booths at every step demanding payment in energy. When we sum the kinetic energy for 500 tons of spacecraft, the power for a megawatt reactor, and the industrial cost of exotic fuels, the bill is staggering. Conservative estimates place the budget for a single, round-trip human mission to Pluto at 1,000 petajoules. That is 1 exajoule, roughly 0.2 of humanity's annual energy outH/FOUT. But converting raw energy into space, ready fuel involves massive inefficiencies. Realistically, a Pluto mission requires an industrial mobilization equivalent to a global conflict, sustained for decades, diverting the Outhanach of nations into the void. This hints at the Great Filter. Why is the universe silent? Perhaps the rocket equation is a quarantine. For heavy biological organisms like us, the outer solar system may be a forbidden zone. We can send our ghosts, our robots, but not our bodies. Consider the alternative. We spend the quadrillions. 6 astronauts arrive after 20 years, old and broken by radiation. They plant a flag on the nitrogen ice, take a photo, and face the terrifying trip home. Was it worth the energy that could have healed Earth? The robot, New Horizons, did the job for a fraction of the cost, without cancer, without hunger. There is hubris in thinking a place isn't explored until a human foot touches it. Pluto belongs to itself. Accepting this is cosmic humility. Earth is an anomaly, a warm, wet paradise. When we leave, we fight a universe that has more energy than we do. The nuclear Leviathan ship is a ghost. It will never be built. Pluto remains silent in the dark, 5 billion kilometers away. Our robots will visit, we will watch, and that must be enough. This ends our journey into the impossible. We dismantled the dream to ground it in reality. Thank you for traveling into the dark. If you found comfort in these limits, or if you simply drifted to sleep, I have done my job. Do you believe we will ever break the laws of physics? Leave your theory below. Hit like and subscribe to support brutal cosmic honesty. Keep looking up, but keep your feet on the ground. This planet is the only ship guaranteed to keep us alive. Good night.